The broadcast is now starting. All attendees are in listen-only mode.
Today.
Unmuted.
As in my role, it's my job to warm up the audience. So I'm going to take a few minutes here to share info on FlexTech with you while we all get settled. Attendees continue to come on the line. So welcome, everyone. FlexTech is a member-supporting technology community within SEMI. We look to connect, educate, and fund companies, universities, and organizations throughout the supply chain, but specifically in the flexible hybrid electronic space. Over our 25-year history, we've launched 3 unique consortium, all of which have technical projects. FlexTech, which was formerly known as the U.S. Display Consortium, was launched in 1993 and was our founding consortium. We've done 222 projects over that time with a combined investment of $237 million. NBMC, let me just say, with FlexTech, we started with the ecosystem for equipment and materials processors for flat panel displays, for that ecosystem. By 2007, we'd morphed into more flexible hybrid electronics and flexible displays. And so over that time, our focus has very much changed in accordance and with the direction from our industry fund, or from our government funding agencies. So that's FlexTech. NBMC, Nanobio Manufacturing Consortium, we launched in 2013. We've done 11 very comprehensive projects in that area. And then, of course, our favorite NextFlex launched in 2015, 165 million over 5 years focused on flexible hybrid electronics manufacturing. And of course, our speaker today is from NextFlex. We integrated operations with SEMI in 2016, thus the hyphenated name, SEMI FlexTech. And if you'd like to learn more about the organization, we've got quite a bit of history at our website at flextech.org. You're welcome to go there. We're a membership organization, and we look to bring value to the industry through any way we can. Standards, advocacy, and policy. In today's uncertain trade environment, we're certainly having a very active role in Washington around the advocacy, but that's really influenced worldwide. We have 7 international offices, regional offices, and these all have connections and policy advocacy work with the governments of those regions. And we also have a very robust market analysis program. We do industry development with technology forums or workforce development. These are big picture industry issues that people at SEMI FlexTech are involved in solving. And of course, we bring specific value to the members. We gather people together of common interest together with our technology communities, of which FlexTech is one of them, MEMS and Sensors Industry Group, another one, Fab Owners Alliance, another one. And some very specific projects on secondary equipment or smart manufacturing. So we have communities that come together to discuss their common issues, their common challenges, but also the ways that we can solve those challenges together and as an industry. We have opportunities to reach key influencers, but also to become one yourself. We have member-only websites and a network of staff ready to assist members in all those regions that have electronic industry activities. So we also bring direct value to our members with discounts that frequently offset their dues, whether it's exhibition space or standard subscriptions, industry data subscriptions, discounts on events and conferences programs. Those are for members. And as I said, frequently offset membership dues. If you have any questions, feel free to contact me or anyone here at SEMI FlexTech that can, or we can give you more information on membership. I would always like to highlight those at times where you can take a leading role in the in the industry, get out there and, as a thought leader, whether it be at our recent, February concluded 2018 Flex in Monterey. Coming up in 2 weeks is Flex Japan, along with the MEMS and Sensors Forum there in Shinagawa. We have our inaugural Flex Taiwan on June 7th, followed quickly by Flex Korea, June 20th through 21st. Very focused on flex displays at Flex Korea. So that's a hot topic there, as well as Taiwan. You can meet, really the people who are active in the industry at those events. And then in the fall, we have Flex China. That'll be our first Flex China in Chengdu. And then Southeast Asia, and then on to Munich and Flex Europa, where the call for papers is currently out. So this is your opportunity to take a leadership role and get up there on the stage and talk about your company and your activities. I encourage you to check that out. Again, the link is at our website, flextech.org. All right, so on to our speaker today is Wilfred Baer. Wilfred is responsible for device integration and system-level hardware projects at NextFlex. Prior to joining NextFlex, Wilfred was at Tango Systems, where he established them as a market leader in the packaging market segment. Wilfred also has been at SÜSS Microtech, where he held a number of positions. And listed below is his technical expertise in packaging processes, next generation solar and energy storage, semiconductor equipment processes, device expertise in a couple of specific application areas. So well qualified to speak to and on our very focused topic today on the Flex Arduino board. Couple of housekeeping items before I turn it over. Since you are registered, you will receive a link to this presentation. We will not be sending out copies of the slides. If you would like either the SEMI or the NextFlex slides, please contact the individual who, Wilfred, Karen, myself, whoever we give the contact info for. And we do expect some time for Q&A at the end of Wilfred's presentation. And since everyone's muted, we're going to use the Q&A box and the Q&A panel in that control panel that you see on your screen. So feel free to enter questions anytime. I'll be coming back on and moderating that. So without further, that's it from me. Sit back, relax, and I will turn it over to Wilfred for the heavy lifting. Wilfred, you should have control. And if you're on mute, good time to unmute. Wilfred, are you there? You were there a few minutes ago. Best laid plans. I believe Wilfred is trying to come back on. We'll give him a few minutes here. Everyone, please bear with us during these. Wilfred, I believe you're moving the slides, but we cannot hear you. Alfred, the system is asking you to enter your audio pin, which I believe was sent to you just a few moments ago. Again, sorry about this, folks. We'll get this solved. There you are. Oh, we heard you for a second. Wilfred, can you hear me?
Okay, can you hear me now?
Yes, excellent.
I've been able to hear you. Okay.
Good.
So for some reason, we didn't really do anything, but it looks like it's active. So sorry for the delay. Thanks for taking time and to listen and see what we can show you about the Flex Arduino project we did. Quickly, a few words on NextFlex. We are a member-based organization.
Muted.
About 80 members at this point, and they really come from different areas to support creating this flexible hybrid electronics infrastructure. It's equipment, contract manufacturing, device component manufacturing, materials, end-use applications like industrial, aerospace, medical devices. So that's just quickly an overview about who we are. We are a public-private partnership with funding from Department of Defense and matching industry funds. And on the next slide, now I don't have control of the slides. Heidi, can you please check on that? I guess everybody can hear me. So here we go. Just a few words on flexible hybrid electronics to explain and identify what this really means. We take printed electronics, which have been around for a long time, has been used for many, let's say, lower-end applications, and we combine it with the processing power of silicon ICs. Instead of printing everything, we're actually attaching high-performance devices on a flexible substrate. So we combine the two, and that's what we call the flexible hybrid. So the hybrid is really attaching components to printed electronics. Next slide. So when you have a new technology like Flex Hybrid that exists in some components, you cannot go to a fab or to a foundry and say, please make this for us. We actually had to create this. So we built the fab and put this into operation about a year ago, Q1 2017, and started bringing in tools and bring up processes. And we initially started with our internal test vehicle to qualify the fab and the processes, but then kind of halfway through switched to the Arduino project as we had the opportunity to build this and use that as our first product demonstrator in our line. And our goal was to take a rigid board, make a standard volume production copper flex board version, and then make the FEG version and compare electrical performance and see if there's any difference between the three versions. Next slide. So just quickly how we are set up. This is our clean room, class 10,000, about 15,000 square feet, and it's separated into printing and additive processing, assembly and integration, and test measurement, characterization, environmental testing in a third area. So here's just some pictures of the equipment we use. See printing on the left, curing, assembly for SMD passives, and die bonder we used for the die attach. And you see some of the clean room operations with testing inspection there. So why Arduino, and what is Arduino? It's an open source, fairly inexpensive, easy to use single class control board that is very widely used in the maker community, education, and increasingly by companies to use as the demo board for systems that build as the actual controller for devices to make. For example, a sensor manufacturer may put their sensor on an Arduino board and use that as a system. So how does Arduino work? There are a few parts that kind of have to fit together. One is there are Arduino boards that you can go online, you just buy the board. Then Arduino provides software that you can load on those boards that enables the functionality of the boards and the attachments and the additional, what they call shields, that can be put on. There's Arduino Create, where you can make your own systems and build functionality with the Arduino boards. If you go on YouTube, you'll find thousands of applications that people build all around the world. And goes from anything, for example, remote control for a small drone, including the controller for the drone itself. So it's a very wide range of functionality you can do. So here is what we did. We took the Arduino Mini Pro that you see on the left and converted it into our final goal, make a flex hybrid electronics board with the same functionality. You can already see the differences between the package components and the die attach and kind of sizes, but that was our end goal. So we broke this down into 3 tasks. And the first task was take the rigid board and create a test board that we can use later on to make the comparison of the different boards, as well as to test the functionality of each board we build. And task 2 was to create the copper flex version, go to a flex board shop, have it built, except for the die attach, do the die attach in-house, do the testing. Task 3 was to build the FEG version with additive processing and attach all components in-house at NextFlex in San Jose. So this is how we got started. We designed the board. You can see it on the right. We converted the BOM from the rigid board to the flex board, put in a lot of functionality into the test board. What you see at the bottom right is the detail on how we can program the board. It's a PogoPin programmer where you can just touch down, load the software directly, or you can do it, as you see in the picture above, through the test board that we created. Here's a closer look on the test board itself. You see that on the top middle we have LEDs and dip switches where we can isolate all the IOs on the IC and actually test each individual IO for functionality as we do bend and flex testing and temperature testing. And we also added a breadboard in the middle so that we can build simple applications for demos. But that was kind of the starting point. The next is, in order to attach a die, we need to know how the die looks like and what the pads sizes are, the pitches are, and get all the dimensions of the die. Since we couldn't get access to wafers for this controller, we simply etched open a die and took all the measurements from there. So next was board layout. So we started with the same board layout you would do for a flex board. But then as we thought about actually doing testing and bending and flex tests, we decided that we need to make 2 changes. One was rearrange the components. So we moved the die, you can see it here, down. We kind of isolate the area. We move the passives up, and all the way to the left, we use the crystal oscillator, which is a metal can and not easy to bend that area. So with that, we created 3 different areas for bend testing: the die attach, the passive attach, and the middle, just to test the printed structures. The last thing we did was we created what we call the wristband design. We actually extended the leads out, make them longer so we can do bend and flex testing easier. And that was our last modification. With that, we went into the copper flex process. So In order to do a project, when you have a new technology wasn't done before, we decided to break it down into sub-projects so we can develop the individual tasks, qualify it, and then move to building the actual boards. So the first was we created SMD, surface mount passive device attach patterns, how we print, how we use the conductive, non-conductive adhesives, optimizing the land designs, the attach area designs for strong adhesion. And we wanted to make sure that we can survive a minimum bend radius and bend cycles before we proceed to building the boards. We did some testing of bumps on the different die versions we used an aerosol jet that we have here for different functionalities. One of them was printing bumps. We tested the die attach and developed the die attach with a daisy chain die that we sourced from On Semiconductor that was specifically designed to enable bend testing on the die and take measurements, resistance measurements of the die as we do testing. And we also ran the FEG substrate through several different printers. We used inkjet, aerosol jet, and screen printing for our evaluation for printing. So kind of the framework for this, when we started the project, we didn't have all the equipment in-house and installed yet that we needed, and our schedule was simply based on the availability of equipment as it comes in and qualified as soon as it gets installed. Of course, not everything was on schedule and took a little bit longer to bring up, but in the end, we managed to get all the equipment functioning the way we needed it. We had also checked all the white papers and talked to other organizations that worked in a space similar to what we do, like the Host Center in the Netherlands, Fraunhofer in Germany, VTT in Finland, and several others, just to understand how those organizations approached it. What we found was nobody really did a direct die attach, so that was fairly unique to our approach. But we learned a few things in terms of process. So here's an example of what we did for the die attach. For the SMD attach. We tested 3 size components, 0402, 0603, 0805. You see the table on the left. And we created a unique way of kind of attaching this landing patterns to make sure that as we do bend testing and cycle tests and temperature testing, that the components will not delaminate. The next step was to do the die attach testing. So here you can see images of the daisy chain die that we used. We actually picked the die size that was very close to the microchip at microcontroller that is in the Arduino board, and used ACP, anisotropic conductive paste. For this assembly project, we used Delo adhesives and did quite extensive testing with daisy chain die. And once we were satisfied with the results we got on the daisy chain die, we moved on to the next assembly steps. So FlexTech Workflow, die preparation, we had to depackage the die for the ICs. In other words, etch out the die, remove the mold compound, etch away the copper bond wires, and then take the die out and use it in our project. We did the flex board design, selected the board shop, did the modifications to match the equipment capabilities of the board shop. Received the copper flex boards, did the die attach, did the encapsulation on the die, and then electrical and bend testing. And once we finished with that, we moved to our next slide. Sorry, so here is lessons learned quickly at CopperFlex. You can see what we built. You can see this wristband design. They have the long leads out, so we can do CopperFlex testing. You can also see very close to the board itself, the contacts, and we can actually cut off the long leads when we are done with the flex testing. We made one change, that's the die attach versus a package attach. On the top right, you can see we had solder mask in the die attach area, which we had to remove. We had to be a little bit creative how we get this off with laser processing, laser ablation. So now to the task 3, the Flex Hybrid build itself. You can see the picture on the left, you can see the die attach. There's actually, this version has a globe top on it, and the passive components on the right, and on the left you can see the crystal oscillator kind of out by its own. So the next slide shows the cross section of a typical FEG system design. You have the substrate, and then top and bottom printing, and using vias, laser drill vias, to make the connection front to back side. Typically, the components are on top. You can see that in green, the microcontroller that we put on, and the discrete components to the right. We can print antennas, we can print batteries or attach batteries on the substrate, and typically on the back side of the device is an adhesive layer that allows for attachment to a structure or biocompatible adhesives for use on skin, for example, for sweat patches, smart wound applications, and other things. We can have microfluidic structures at the bottom of the device, as you can see on the left side, or it can be textile integration directly on fabrics. So that's a kind of a typical approach on how we design FEG. So on the next slide, you can see kind of an overview of the process steps. So first, system design, system layout. We print the substrate. We do a flip chip die attach. We use pick and place to attach the passive components, and then we do passivation. We did some experiments with passivation, but we did not do a system passivation, and then we do flex testing, bend testing, and environmental testing, UV, temperature cycling, and all the standard tests you would do. Next slide. So here's a process flow a little bit more in detail. And we really have two build areas and two unit processes. One is print, and you see the pre-treat substrates, laser drill the vias, then we print the top layer, we do thermal curing, and we do the bottom layer, print, thermal curing, and then last step is we do a visual inspection for print quality. We do continuity tests on the substrates before we hand them off to assembly. In assembly, we take die either from background tape, if it's in wafer form, or out of waffle pack or gel pack, if it's in individual components, and place it on the substrate. Then we take either waffle pack or tape and reel for the passives and attach the passives. The dispense for the conductive paste for die attach is done in the die bonder. For the passives, we have a separate dispense system for the conductive and non-conductive adhesives. Next. So here's a typical board process comparison. So if you build a rigid board, you have 19 process steps. And you can see it up there, how the standard process is done. If you make an FEG board, you have 7 process steps. So the 7 process steps by itself make it a lot less expensive than what we have on a rigid board approach. So when we selected the processes, we found a few very interesting things. One is, since we make the hybrid approach, we combine printing and assembly, and we started out with optimizing print. And we found substrate and ink combinations that worked very well. The ink wouldn't flow or spread after printing, and we get very good electrical properties. And then we started to use the adhesives and attach the components. As it turned out, some of the best print or substrate and ink combinations would not work at all for assembly. For example, if the solvent gets removed quickly during printing due to the substrate properties, this doesn't work at all for adhesives. As soon as you put the adhesive down, all the solvent is removed as well and has no more ability to actually attach components. So we had to restart and really understand the link and interaction between the print substrates, inks, and the assembly components to make it work as a system. So first step is printing, and we used several different printers to see which one works best for the application, gives us the electrical and mechanical properties, and also works in conjunction with the assembly process. So you see some of those equipments here: Meyer Burger inkjet printers, Dynamics inkjet printers, Optomec aerosol jet. And you can also see adhesives. We used ACI, Novocentrics, inks, Dado adhesives. And list of the inks: DuPont, EMS, Agfa, ACI Materials, Novocentrics, were the ones evaluated during the process development. Next. So here you can see two prints that were done with, let's say, non-standard printing methods. To the left is an aerosol jet, and to the right is an inkjet pattern. And both work very well, except that the thicknesses we needed were more in the 6 to 8 micron range, and we would achieve about 1 micron on those two print methods. So we actually switched to screen printing for our FEG builds. Here's an example of how the printing looks like once the dielectrics are on. So you see the dielectric in blue, front side and back side. And these substrates get inspected and then moved to assembly. So the process flow we picked for the FEG device was we do screen print for the silver traces, and start out with laser drilling, then we print, screen print top, screen print bottom for the conductors, and then we put the dielectric insulating layers on. The next is component attach, ACP dispense, and die attach with flash cure. Then we dispense the conductive, non-conductive adhesives for SMD components, and then we encapsulate the individual components. And then third part is we take the singulated devices and do electrical testing on the test board, and then do mechanical test with manual testing. So here's a comparison just based on weight, not even looking at form factor between the different devices. To the left is the Arduino, which is the Arduino Uno, which is the most popular Arduino board, and has fairly large connectors and components, and weighs about 28 grams. If you take the Arduino Mini, that's 2 grams, so it's a very small board to begin with. If you look at the CopperFlex, that's 0.69, and the FEG version 0.65. So you can see how quickly the weight goes down by using a flex board and flex application. We did use the same bill of materials, the same components, but the next step will be is that we actually print some of the passives instead of attaching them, which will further reduce the size and the weight of the FEG devices. So some of the lessons learned was really about interactions between inks, adhesives, substrates that were a lot more challenging than we initially thought. And from starting up with kind of optimizing the individual process steps, we then had to redo this and really make the whole process flow work and optimize all of the process steps to get the results we're looking for. And for example, in particular, some of the SMT attach methods that are common practice today with solder attach are kind of counterintuitive, or what we have to do with adhesives is counterintuitive to what is done in packaging today. So we had to overcome this as well by completely changing the approach on how those passives are attached. So here you see a selection of samples built. You see CopperFlex to the left, and these were all tested and flex tested, electrically tested on the test boards. And on the right to carriers, you see different versions of FEG builds. We did PET, polyester as a substrate, and we did polyimide, PI as substrate as well. And we used different ink and substrate combinations. We actually had a fairly extensive TOE in our final builds. So here's an example of what we did for development. Our standard substrate size is 8 by 12 inches, and for development, we simply put between 4 and 6 of the Flex Arduinos on a substrate. When we actually go to production and build in volume, then we would pack the units fairly densely on a substrate, as you can see on the right, and do the same processes, laser drilling, printing, both sides, component assembly, and then test, and simulation based on a layout that looks very similar to what you see on the right. So what are we going to change and do differently on our Gen 2 version, which we have in the planning phase right now, and we'll start officially in a few weeks. So the first is from a board layout perspective. We'll actually look at the bill of materials and look at component sizing, part count, and the ability to add on other components that are currently not on the Arduino board. So for example, component sizing, different resistor capacitor sizes work better with adhesive attach on additively manufactured boards than others. So we found, for example, that for 0402, there's a specific design that we need to do to make this component work
Unmuted.
in flex sizes. We'll also look at the component list itself to see what we can print, and also see if we really need all the components that are on the rigid board. And that will reduce the board area, reduce the weight, and also improve the ability to flex the overall system and make it possible for smaller band radii. The second is for die attach. We did a flip chip type face down approach. We'll also use a print up version of an ultra thin die, so we can actually print on the substrate the top of the pad when we do a face up design. It's kind of like wire bonding, but using 3D printing with silver inks instead. We'll continue to optimize our passive attach, and we will work both on the component encapsulation as well as on the system encapsulation, so that we can go through humidity testing and kind of make it a very rugged system for different environments. When we picked the connectors in our first version, we actually made used the very small connectors that are typically used for those CopperFlex boards. Very small ZIF connectors, 0 insertion force. But as we found out, they're not necessarily the most user-friendly connectors. So the next version will have much larger connectors and also much wider traces out of the boards. So the next part is functionality enhancement. We took a basic board and converted it into Flex to demonstrate the process and the ability to do that. And as we found out, many people have tried this, but nobody really made it work. So we were the first ones to actually make the Flex Arduinos function, you can repeatedly build them and go through standard test cycles and make the substrate survive in that. So wireless connectivity is one of the key things we want to add. Low power Bluetooth, either as an SoC, silicon, a system on chip, or as a dedicated IC in addition to the microcontroller. Both options are evaluated, are feasible, just need to decide what makes the most sense from an interconnect perspective. Second is, we're planning on adding power directly to the board itself. And it can be a rechargeable battery, it can be a replaceable battery. Ideally, it's rechargeable and wireless charging. And just need to work on the individual component developments, for example, printing cores to enable the wireless charging. And the third part is to enable the modularity and building blocks so that components can be easily attached to the base Arduino board. And as an example, just to visualize that, you have a connector on one side, not like on both ends as we had it now, and have the connector on one side and have the ability to attach other flex boards, for example, with sensors on it, or directly attach on the board, or print on the board sensors, antennas, and other things that might be useful in the application itself or needed in the application. So that's kind of an overview of what the next steps are, what the next generation will look like. So, huge acknowledgements. Many thanks to our fab team for making it possible, bringing up equipment, learning it very quickly, and actually making the devices work, as well as to our material suppliers that helped us with specific materials, some of them not even released to market yet: DuPont, Agfa, Novacentrix, Delo, EMS Connectec, and particular thanks to ESI for helping us with laser processing while their laser was getting ready to be installed at our facility. They actually helped us do most of the laser processing in their applications lab. And with this, thank you very much. And if you have any questions, ready to questions.
All right, thanks, Wilfred.
Sure.
Great walkthrough of the process and good example of how the NextFlex facility is working. Hopefully that gave folks on the line a good run through of what they were looking for. So we have a couple of questions, couple focused on business, some on technical. We'll start off with some of the easy ones. How does one buy a Flex Arduino sample from NextFlex or get one?
So at this point, we are working with the Arduino organization to make Flex Arduinos available to the public. So the goal would be is that we continue to work with them to actually, make Arduino boards that can be made available through the standard Arduino channels. Our first samples were really built for creating a test platform, and at this point, we are not providing any samples for our first generation, but we plan to do so for generation 2 as it becomes available in maybe by the end of the year.
Great. Okay. How about, do you have a cost estimate for that?
Our first ones are really expensive, so very expensive. So from a cost perspective, it will be in the range that rigid boards are. Ultimately, once it goes into high volume, the Flex hybrid electronics boards will be less expensive than rigid boards. So that is simply a matter of volume and getting this into a very optimized process flow. And as you can see from the presentation earlier, we have a very short or a very minimized number of process steps compared to standard rigid boards. And I think the two parts that will really drive the cost down is optimization of each of the process steps and just getting it into volume to drive out all the cost elements and get it to desired low cost levels, and really from a functionality perspective, make it the IoT enabling platforms that have been missing in that space for a long time.
Great. And I think you touched on this a little bit. Are you planning to manufacture the boards, the flexible Arduino boards?
So we will manufacture the boards in-house until we are ready to hand it off to a contract manufacturer that can do this in very high volume. And our fab has production tools, so we don't have R&D tools that need to be, where we need to transfer processes into production tools. We actually have all production tools that allow us to transfer directly with our recipes and material parameters into a high volume manufacturing environment, which is really the phase once we put out the first several thousand units from our fab, or maybe tens of thousands, depending on how quickly we can get the contract manufacturers up and running.
Good. All right. I think that's, thanks for leaving so much time, because now let's move on to the technical questions.
Sure.
Okay. Did you have any specific reason for using conductive adhesives and not solder for the SMT component attach?
Yes, there are actually several reasons. So the first one is when you use PET polyester, the temperature, the processing temperature that the substrate allows is much, much lower than you need for solder. And the second is when you do flex testing, solder is not the best material for flexing the interconnect. So the adhesives have much better properties to do so. And I think from a flexibility perspective, when we use PI, it is possible to use solder, but we set up a process flow that can be used for any substrate out there. And from a cost perspective, reducing the number of steps, reducing process temperatures, reduces cost and increases reliability.
Good. Okay. Have you completed either radius or curvature, functional or extended temperature testing of the products?
So we have tested both all the sub project developments for SMD attach and the die attach over varying band radius. We started with 32 millimeters, went to 20 and 10 millimeters. So in the end, everything we tested was at a 10 millimeter band radius. And each board was tested for at least 50 cycles. And the main failure mode we found was not in the die attach, but was actually in the passive attach area, in particular with the crystal oscillator. And we were concerned about that and actually moved it to its isolated space. And as it turned out, it was the first part to fail. We did UV testing, standard daylight 1 testing, and we did temperature cycling for consumer temperature ranges.
How does this come out in a report? How will that be available, the answers to these kind of questions, other than in this webinar? Presentation, or are you issuing something?
So there is no specific plan at this point to give out the details outside of our membership base. And the project was funded by AFRL, the Air Force Research Lab, and a very detailed report on all the process developments and functionality was given to AFRL, and it's within their decision to provide details on the project beyond of what you have seen here.
All right, thanks. Bluetooth module. Which Bluetooth module is best suited for the flexible substrate?
That is a very good question. So we have really two options, as I had shown in the slide earlier. One is to take an SoC, system on chip module, and integrate that. The advantage is that it's only one die attach, it's combined. The other option is to take a standard microcontroller, Atmega like we had it now, or similar, and add a separate Bluetooth IC. So we have a 2 die attach process. Of course, 1 die attach is simpler, but in most cases, the SoC will have a smaller pad pitch, smaller pad areas than the 2 separate ICs. And we're in the process of evaluating which one will be more reliable and lower cost to print to. Because the finer the print features, in the end, the more costly the process. But those are the 2 avenues we'll pursue, and there are several suppliers out there that have very good low power Bluetooth ICs.
Okay. Back to die attach. Does the die attach limit the speed of the SoC?
If the die attach is done properly with the right ACP combination that's suited for the conductors, we did not see any difference. We did evaluate, just on that note, about 5 different ACPs to see which one works, varying by particle size and chemistry. And it is important to select the ACP or the conductive anisotropic conductive paste that works with the specific conductor print material that we use. So it's not, you can use any ACP or any print and it will work together. That's a very specific combination and selection. But once it's done right, it works. No change.
Okay. Can you please let us know the manufacturing cycle time?
So, of course, in our first development, we took a very long time to run each cycle because we had to set up the tools. Just as a comparison, the die attach capability on our die bonder is about between 6,000 and 8,000 units per hour, depending on the thickness and speed we can place it. And our pick and place tool for passives can do about 14,000 units an hour. So that's kind of the assembly side of it. And if we print, it really depends on what print method we use. We can screen print 1 8x12 sheet typically every 30 seconds. So it's a fairly fast process.
Good, okay. Can you please comment how you address the heat, I think, dissipation in the printed flex printed circuit board?
So I take it the question is related to the IC on board and how we spread the heat. That is part of the encapsulation process and also part of the protective layers that we put on top of it. So that's really a system design, and that varies by component that we integrate depending on the temperatures that we expect to see.
Okay. Do you think screen printing will remain the standard process once it's in mass production?
So we used screen printing because it gave us the desired thickness of conductive material very quickly, and we used it in combination with laser ablation to create the fine features we needed. And the process works well. We have both inkjet and, for example, gravure offset that have very high promise to be a scalable digital printing method, but it takes work to achieve the thicknesses we need for the conductive materials. We simply, from a time perspective, used screen printing because that worked, and the other print methods need more development effort to get there. But our plan is to actually go to a digital manufacturing flow where we can simply create a file, send it to the printer and print. Kind of in an ideal case, compare it to, let's say, in an office environment, you print a document, it goes to the printer, comes out, and you can do 1 or you can do 500. It doesn't really require any change in setup. That's the goal for our printing approach. So in the end, if you think about creating peel and stick electronics that you print on a sheet of substrate, and you have adhesive backing on the back, you just peel it off and place it wherever you need it. And you can have low cost, but also high mix in terms of what you build.
All right. How thick can the chip be? Any limitation on the die size for quality issues?
So what we found was that the typical die sizes for the microcontrollers we're looking at are in the 2.5 to 4 millimeter side length. So almost everything we looked at is less than 5 by 5 millimeters. In this project, we used the standard thickness die, 180 micron as it came out of the package. But we have done qualification of pick and place of ultra-thin die on our die bonder, and we can do 50 micron quite readily and very high yielding. And we are right now in the process of qualifying a 30 micron die process. So this is primarily a handling issue, and attach requires some customization on the tooling itself to process ultra-thin die. But those are the two thickness ranges we're looking at, 50 and 30 micron die, and handling a standard thickness die is actually fairly straightforward.
Okay. All right. How does a member sign up for samples to try this out?
I think that's really for our next phase of build, and in that we need to kind of work with the members directly to give them access to what we built.
Okay, so contact you directly. You guys will be managing a list of people interested, or you'll know from the membership meetings?
Yes, absolutely. We'll communicate this within the member base.
Okay. Do you plan on beta testing in the field at facilities? For example, investigating the using this in a smart factory innovation?
Okay, sorry, I'm not.
Can
you repeat the question?
Yeah, it sounds like maybe an application question for creating the next step, the product that you use the Arduino for. So let's hold on that. How can we monitor progress on this project as it continues?
So the project itself will continue. We have a very high level of interest. Actually, surprisingly, we didn't really, see at the beginning how big this interest would be. We kind of thought we opened the door a little bit and get our foot in there and just built the first Arduino like board. But we didn't realize how long the line was on the other side of the door of people interested in this. So we are incorporating this into the next generation of builds that we make higher number of devices and make them available. In particular for our effort on workforce development, getting into the hands of students and education. You will find more information about our next plans in our newsletter, and you can go on our website, www.nextflex.us, and get the updates on our next steps on the Arduino project.
All right, we got 1 minute, so one last question. Any creative method to bypass the bump process?
So when we did the builds for the FEG versions, we actually did both bumped and non-bumped die, and both work, but they don't work with any ink. So specific inks we can attach without bumps, and some others we do need bumps. So we are evaluating these approaches. And we had also worked with one of our members, FlexTech, the Japanese manufacturer of materials, to print bumps directly on the substrate. And they actually did a build of some of our copper flex samples where they printed bumps on the substrate. So that's also a path that's possible.
All right. Well, we are at 9 o'clock, and that's it for the questions. I want to thank Wilfred a lot for putting this on and bearing with us during the technical troubles. And thank you, team at NextFlex. And everybody stay in touch. Stay in touch to learn more about this. We have your email addresses, and you will receive a thank you as well as the link to rewatch this video, or it'll be a video, and have some more time to understand the process. So thanks a lot, Wilfred. Thanks everybody for joining us, and we'll see you next time. Bye.
Thank you.
Bye.
Bye.